So, in 1972, the Club of Rome proposed a report titled Limits to Growth. So, since at least 1972, we've been making the argument that there have to be limits to growth, that we live on a finite planet, and that as such, it is impossible for us to keep on growing materially in the material world. If you think of growth as flows of matter, energy, and information, matter is physical, it takes up space. So the readings that we have for this week are three. Uh, the first one is by Goodland, is written in 1992. The second one by Rockstrom is 2009. And the one by Daly is sort of an organizing one that lays out the concepts that you need to understand to get a grasp on the idea of limits to growth. Okay, so let's take Goodland first, and let's talk about what Goodland is talking about. The diagram that he shows, which is about the ecosystem, and the argument that he makes that we start from a state in which the human economy is a relatively small subset of the ecosphere, right? And that over time, the human economy has grown to take up more and more of ecospheric space until it's beginning to overwhelm the ecosystem. Um, Within that picture of a growing human economy, what Goodland says is that there is an argument to be made for limits to growth. Think about this. You have finite resources, all right? Take any one resource that's a finite resource. Let's say oil. There is a time in human history when oil extraction is at zero. We've not yet discovered oil, we've not started to use it, it's still buried in the ground, extraction is at zero. There'll be another point in human history where oil is at zero again because we've used up all the oil that there is. This is some hypothetical point in the future, right? If you visualize a graph that lays out this dynamic with two zeros established, one in the past and one somewhere in the future, then the question is what happens between the two zeros? And what you end up with is some kind of an inverted U-shaped graph. There could be multiple peaks, there could be variations on the theme, but basically the use of that finite resource will increase and then will begin to slow down and then will begin to decline and at some point will hit zero. This is it's a straight logical exercise in finite resource extraction. Goodland's argument is that there have to be limits to growth simply because we live on one planet. And there isn't another planet that we can go to that would help us get a handle on what it is that we're trying to do here. So, taken in this context, what you have to understand from Goodland is that, um, well, let me come at it differently. Goodland presents five evidence structures that indicate that we have already pushed the limits to growth, that we have exceeded the limits to healthy growth, that we need to downscale throughput growth before we can begin to talk about sustainability in any meaningful way. So he talks about biomass appropriation, global climate change, ozone hole rupture, land degradation, biodiversity, and then he spends some time talking about population. In these five cases that he presents to us, where he tries to demonstrate that there is in fact an exceedance of the limits, uh, the argument that he's trying to make is, in the case of biomass appropriation, for instance, what he suggests is, do you folks understand net primary productivity? Okay, let me explain this briefly. Um, the planet is a finite space. There is only one kind of input and that's radiation from space, solar radiation and some cosmic rays and so on and so forth. That's the only input into the system. Okay, so this solar radiation that comes into the planet strikes the planet's surface and encounters green stuff, biomass, okay, where magically chlorophyll interacts with sunlight through a process called photosynthesis to create biomass. This is the only source of growth on the planet left to its own devices. Okay? The amount of biomass that is created in a year is called primary productivity. The amount of biomass that is left over from what the plants need for their own sustenance, for their own health, their own growth, is net primary productivity. This is the surplus that is available to all life forms on the planet as food source. And it is the surplus that defines how much of primary productivity is available to us to use for our own purposes. So, think about this. Currently, by Vitusek's estimates, we are using roughly 40% of net primary productivity for human purposes. Our food crops, the biomass that we use for processing goods and services, meat and feedstock for our meat, chickens, egg, poultry, uh, pigs, goats, um, beef, and so on and so forth. All the uses that we make of net primary productivity, humans are consuming roughly 40%. Okay, this is the evidence that Vitusek presents. It's debatable, but it's a reasonable number to start with. Let me give you another factoid. There is another species on this planet that is voracious in its consumption of biomass, and that is termites. Termites are everywhere on this planet. On every continent, you will find termites. And termites eat non-stop. They're at it day in and day out, 24/7, 365. They don't stop, they don't take a break, they eat. That's what termites do. Termites are consuming roughly, best estimate that we have, about 30% of net primary productivity. So humans and termites between us are consuming 70% of net primary productivity. And this is estimated in 1992, mind you, 20 years back. So it's probably worse now than it was then. But let's go with the 1992 numbers. So 70% of net primary productivity has been co-opted by two species, humans and termites. 30% of net primary productivity is left over for every other species on this planet. All other life forms get 30%, we get 40%, termites get 30%. Think about that for a moment. What does that say about sustainability? What are we going to do about this world in which we live? Right? Then he goes on to talk about global climate change. I don't know where you guys are individually with global climate change. There's this supposed to be this big debate about whether climate change is real or not. Um, all I will say to you is this, and I'd like you to think about it. Since life began on this planet, the sun has gotten 30% hotter. The sun is a nuclear reaction. It's getting hotter all the time. Okay? The sun is getting hotter constantly. So, since life began on this planet, the sun has gotten 30% hotter. We can know this with certainty. This is physics. There's no models that are required. to estimate this. We can tell this from the properties of the sun and the nuclear properties of a nuclear reaction. However, since life began on this planet, the planet itself has not gotten 30% hotter. We can be sure of this as well. There have been fluctuations in temperature, there have been ice ages, there have been all this stuff, but the fluctuation in global mean temperature has been in the order of 1 to 2 degrees centigrade. Okay? By and large, this, the temperature of the planet has not increased over the last 30 years. How can this be that the sun is getting hotter and the planet is not? How can this be? There's only one explanation, and that has to do with greenhouse gases. The upper atmosphere contains greenhouse gases. Sunlight comes in, hits the planet's surface, is reflected out as infrared, hits the greenhouse gases, bounces back in. It gets trapped. Okay? So, while the sun has been getting hotter, the planet has been getting cooler to offset the sun's heat. The only way it can do that is by pumping down carbon dioxide from the upper atmosphere and sucking it into the oceans and sinking it to the ocean floor. And I can show you videos that will demonstrate this quite clearly. So this is just fact. If that's true, then what we are doing since the Industrial Revolution is taking carbon from below ground, fossil fuels, and pumping it into the upper atmosphere. Absolutely the opposite of what the planet needs, absolutely the opposite of what is needed in the face of the sun getting hotter. We are reversing the trend. This is the source of global climate change. From today, do you know what it would take for another ice age to hit? If global mean temperature fell by 3 degrees centigrade, 3 to 4 degrees centigrade, that's it. We'd get an ice age. So if global mean temperature increases by 3 to 4 degrees centigrade, which is what we're looking at currently, what are you looking at? Global warming. Simply fact. Okay? We already passed the thresholds of radical change. Now the question is not mitigation, now the question is adaptation. How do we live in the context of a warming planet? The third piece he looks at is the ozone hole. Tropospheric ozone is different from stratospheric ozone. Tropospheric ozone is smog. This is pollution. This is bad. Stratospheric ozone in the upper atmosphere is a good thing because it keeps out UV radiation from the sun, keeps us from getting sunburned. There is a hole in the ozone layer, in the stratospheric ozone layer, that is being caused by chemicals that we call chlorofluorocarbons and other ozone eating chemicals that we are emitting at the surface of the planet. Gradually these rise to the stratosphere, and when they get to the stratosphere they begin to destroy ozone in the stratospheric layer. As the ozone gets destroyed, the ability of the planet to shield us from ultraviolet radiation gets diminished, and you begin to get cancers, and you begin to get changes in ecosystems, and you begin to get changes in planetary processes that are not good for us. The third piece he talks about is land degradation. We consume roughly 2% of available land surface on the planet, but we are transforming land areas far in excess of the areas that we inhabit. Our cities, towns, and villages consume a relatively small proportion of land mass. But deforestation, desertification, impervious surfaces, all these kinds of forces are busy transforming land and degrading the quality of the land and its ability to sustain us. Biodiversity. As we destroy habitat, we destroy the capacity of a habitat to sustain life, and we begin to destroy um, biodiversity. We are we have had, since the beginning of the planet, we have had five mass extinctions. The most recent of these was the extinction of the dinosaurs. Okay, so the planet has seen mass extinctions before, and the planet is still here.